In this lesson, we're going to be discussing the derivative from first principle, which is in fact the mathematical definition of a derivative. Now, in previous lessons, we have tackled differentiation rules that would help us determine the derivative of a given function. And we've also seen that the derivative at a given point is in fact the slope of a tangent at that point. And now the derivative from first principle is what help us know why. Why is it that the derivative at a given point is the slope of the tangent at that point? And why is it that these derivative rules or differentiation rules do apply? Now, I'm going to start by considering this function, this curve, and we have the point A of coordinates of abscissa A and ordinate f of A. Now, we consider another point M on the curve where the abscissa of M is in fact A plus H. So, in order to get to M, I do add H to the abscissa of A, So the ordinate of M would in fact be f of A plus H. Now, if we look at this, if we consider over here, you can actually see the segment joining A and M. So looking at the segment joining A and M, and looking at the tangent T, the tangent to the curve at x equals to A, you notice that the segment AM, which is the rate of change between A and M on the curve. However, if you look at them, the rate of change here is in fact not exactly equal to the slope of the tangent. They are two lines with completely different slopes or directions. However, as h approaches 0, now h is not exactly a 0, it approaches 0. So as h approaches 0, you'd notice that point M would be infinitely getting closer to point A. And as M becomes too close to point A, notice that the segment AM, which is the rate of change of the curve between A and M, segment AM would almost become confounded with the tangent. So AM and the tangent would now have the same slope. So this is why the rate of change between 2 points on a curve defined by the derivative at point A would in fact be equal to the slope of that increment following A. So now that segment AM and the tangent T at point A are almost confounded, in that case, f prime of A would actually be the limit when h is approaching 0 of the slope of that segment. And the slope of segment AM is defined by y of M minus y of A over x of M minus x of A. Y of M is f of A plus h, y of A is f of A, and divided by the difference between the two abscissas, which is h. So that is the derivative from first principle of a given function at a given point of abscissa A. So f prime of A is in fact equals to this limit of this function when h is approaching 0. Okay, now in order to put this into an example here, we need to find the gradient of the curve of y equals to x squared at x equals to negative 2. Now, the gradient is in fact the same as the derivative at that point. So what they're asking for here is in fact f prime of negative 2, given that f of x is x squared. Of course, you cannot use f prime if you have not called the function f. In that case, you just use Newton's notation dy over dx at x equals to negative 2. However, if I let f of x to be equals to x squared, and I need to find f prime of negative 2 from first principle. Now, of course, if the question does not really ask for the gradient from first principle, you could just apply the derivative rule. The derivative rule, in fact, implies that if f of x is x squared, f prime of x is 2x, in that case, f prime of negative 2 would in fact be equals to negative 4. So now I know for a fact that when I apply the derivative from first principle, I'm going to end up with f prime of negative 2 equals to negative 4. So if in the question they do ask for the derivative from first principle, you'd have to use the definition of the derivative using the limit. If they don't ask for it from first principle, in that case, you could just use the derivative rules. Now over here, it's the limit when h is approaching 0 of f of negative 2 plus h minus f of negative 2 over h. Now over here, replacing x by negative 2 plus h, evaluating f of negative 2 plus h, that would in fact be the limit when h is approaching 0 of negative 2 plus h all squared, which is equivalent to h minus 2 all squared, minus f of negative 2, which is negative 2 squared, which is a 4, divided by h. Now over here, since this is a difference of 2 squared, you could either choose to expand or factorize. Now of course, expanding is easier. It's h squared minus 4h plus 4 minus 4 over h. 4 minus 4, the 4's cancel out. I'd have h squared minus 4h over h. Now that is a 0 over 0. Now I could use L'Hopital's rule here since it's a 0 over 0 in order to find this limit. Or I could just notice that h is a common factor at the numerator, so I could just factor it out, which leaves me with h into h minus 4 over h, and then cancel out the h. Then limit when h is approaching 0 of h minus 4, and then replacing 0 for h would actually give me the negative 4 I know that I have to reach. Now, just on a quick note that the derivative from first principle, since f prime of a is in fact a limit, if this limit does not exist, it means that the derivative does not exist at that point, which means that the function is not differentiable at that point. Now, going through the second example, I need to find the points of the function or the curve of equation y equals to 1 over x, where the gradient is negative 1 over 9. So in order to find the points, I need to find the points of coordinates xy, where the gradient is negative 1 over 9. And we know that the gradient is in fact the derivative. So I need to find x for which f prime of x is negative 1 over 9. Now I need to find f prime of x first. Now we know that f prime of x is negative 1 over x squared when f is 1 over x. So if f is 1 over x, in that case, f prime of x is negative 1 over x. That is because of the derivative rules that you already know. However, since over here we need to use the limit from the derivative of the function from first principle, then I need to find f prime of x using that limit from first principle. So it's f of x plus h minus f of x over h. Now, replacing and simplifying and finding what that limit is in fact equals to, f of x plus h is 1 over x plus h, of course given that f of x is 1 over x, minus 1 over x over h. At the numerator, reducing to the same denominator, I would have x minus into x plus h over xh into x plus h. Now the common denominator here is x into x plus h, which drops down to this denominator, which leaves me with xh into x plus h. So f prime of x would in fact be x minus x is 0 and minus h, so that's the limit when h is approaching 0 of negative h over xh into x plus h. Now the h cancels out, and I'm left with the limit when h is approaching 0 of negative 1 over x into x plus h. Now applying 0 for h, that would leave me with negative 1 over x squared, which is the derivative that you already know for 1 over x. So now that I have found f prime of x, I go back here and replace. So negative 1 over x squared equals to negative 1 over 9 leads to x squared equals 9, which leads to x equals to 3 or x equals to negative 3. Now, since they asked for a point, the point is in fact an ordered pair. It consists of an ordered pair, x, y. So over here, x equals to 3. So in order to find y, I replace in the given function x by 3. So y here in fact is 1/3, and y here in fact is negative 1/3. So the 2 points we're looking for are 3 and 1/3 and negative 3, negative 1/3. So these are 2 points on this curve where the gradient is negative 1 over 9. I remind you that the gradient is the derivative, which is the slope of the tangent at that given point. Now, given that f of x is 2x squared plus x, use the derivative from first principle to determine f prime x. Now, I would just like to note quickly that in the 2 previous examples, the question does not really tell us specifically to use the derivative from first principle. In that case, you could use the derivative rules immediately, okay? But I did use the derivative from first principle in order for you to see how it actually applies. However, when the question does ask for the derivative from first principle, you'd have to apply the derivative from first principle. You cannot use the derivative rules. So I need to find f prime of x, given that f of x is 2x squared plus x. Now, over here, on a quick note, f prime of x, what's the derivative of 2x squared plus x if I were to be using the derivative rules? 2x squared has a derivative of 4x, and x has a derivative of 1. So when I use the derivative from first principle, I know that I will reach an expression equals to 4x plus 1. So let's just start with the definition of the derivative from first principle. So it's the limit when h is approaching 0 of fx plus h minus f of x over h. And now given that f of x is this function, so I replace at the numerator, so it's 2 into x plus h all squared plus x plus h. So whatever I have x, I replace by x plus h minus f of x, the expression as is, divided by h. And over here I forgot the limit when h is approaching 0. As long as I have not replaced the variable by the value it's approaching, I have to keep writing limit when h is approaching 0. So over here, expanding and simplifying, I'm going to expand x plus h all squared, multiply by 2 immediately. So it's x squared times 2, which is 2x squared, then 2xh times 2, which is 4xh, h squared times 2, which is 2h squared, plus x plus h minus 2x squared minus x, expanding the negative into f of x. Now the limit when h is approaching 0 of. Now looking for common factors here, you'd notice that 2x squared minus 2x squared, they cancel out. X minus x, they also cancel out, which leaves me with these three terms where h is a common factor. So I factor out h, I'd have 4x left here, 2h left from 2h squared, and a 1. h, when I factor out h, I'd have a 1 left divided by h, and then I cancel out the h. So the limit when h is approaching 0 of 4x plus 2h plus 1. Now applying 0 for h, 2h would in fact be equals to 0, and I'd end up with 4x plus 1 as f prime of x, which I already know this is the derivative that I'm looking for. So in fact, when the question asks you to use the derivative from first principle, you'd have to use the derivative from first principle. If it doesn't ask you to use the derivative from first principle, you don't really have to use it. It would be a lot easier to use the derivative rules. So that is it regarding the derivative from first principle. As you can see, it does justify the differentiation rules that you already know how to in fact use.